Now on to the low PRF example, moving target detector. By the way, this particular example of the moving target detector, you'll find in Skolnick's book, his handbook. It's just about every radar book since the 80s that's come out devotes a section or a number of pages to describing the technology of this process, and it's pretty much used in all low PRF ground-based radars. So in this particular case, we have 1,000 range cells, as I mentioned earlier, 500 azimuth cells, and these aren't azimuth beam widths, they're CPIs, and 8 to 10 Doppler cells, and it gives us the order of about 5 million range azimuth Doppler cells every 5 seconds that we're going to process and independently threshold. And we're dealing with a 1/16 of a nautical mile range resolution, range of the radar of 60 nautical miles, and that's just one of the range azimuth cells, and within that range azimuth cell, we're going to process it through the order of 8 or 10 pulses. In the implementation of the MTD, we processed 10 pulses and came out with 8 filters, which did the job quite nicely. And here we see the beam going around at 4.7 RPM. Excuse me, that's the number of seconds to go around at approximately 12 RPM, 1250 hertz, 1.2 degrees is about the beam width. And we get about 22 pulses per beam width. So you're in good shape, you get 2 PRFs. Now the moving target detector wanted to solve these problems. It wanted to solve the ground clutter problem, and it does this by 8 pulse Doppler linear coherent filters, which are made up of a total of 10 pulses. We handle second time around clutter with a coherent transmitter and a constant PRF within the coherent processing interval. That means no staggered PRFs. We handle rain with a Doppler filter bank, and we adaptively threshold for each range azimuth Doppler cell 3.9 million cells. In the example before, it's about 5, I have to say, but it's about 3.9. It depends on which version of different radars, how they're divided up. But the order of 4 or 5 million cells. And tangential targets are handled with a fine-grained clutter map. I'll go into the details of that clutter map. And blind speeds are handled by sending out 2 CPIs with different PRFs. You don't see it in one, you'll see it in the other. And there's a neat trick that was invented by Ed Mewey, the inventor of the MTD concept. And here, in this block diagram, is the essence of the MTD. You've got I and Q coming in, and this is that linear Doppler filter, which you're going to see is implemented. Initially, it was implemented with a bunch of different easy-to-implement things with chips, and a second implementation went to a programmable processor, and now you can implement it. This whole business from here to here on an ASR7 with 5 or 6 power PC computers, and then the post-processing with another one. We have 8 or greater pulse Doppler filter bank, a 0 velocity filter and a filter map, which I'll describe, and then the adaptive thresholding for each cell, and then post-processing thresholding to get rid of birds and ground traffic that eke their way through. And I've gone over that in these words with you so far. Okay. Now here's a picture of that ASR7, and these are the ASR9 filter bank. Exactly what is used in the ASR9. And here we see one of the filters, and say we have an aircraft that isn't at 30 miles an hour, but let's say is at 140 miles an hour, it will alias down because the blind speed, and it will fall into this filter. And if we have rain up here, and notice the rain echoes are down approximately 40 dB from the peak response, this rain will get rejected so that after the filtering, the aircraft is cleanly seen. And having a whole bank of filters like that gives you the opportunity for the aircraft, not only if they're from 0 to 100 knots, but to keep aliasing down. And in one of the two cases, you'll probably alias into a filter. The odds are very high that will be within the pass band of one of the filters. And this is how the trick works. Here's how we send out PRF1, and you see we have PRF2. And here's the radial velocity of the rain, something like that. We have a true aircraft velocity here that's beyond the blind speed of this PRF or this PRF with a longer blind speed. Well, this CPI will alias down to right here, and the detections at the CPI, this CPI, will alias down here. So in this case, the target would be competing with the rain's velocity distribution, whereas at this coherent processing interval with its uniquely different PRF from the other, it would come down and you'd be competing against noise. So that was the insight that Ed Muey had to deal with rain in this small Doppler space at S-band from aliasing targets and using what we call here multiple PRFs. And here's the proof that's in the proof is in the pudding, really. And on August of 1975, this is the result of about 40 scans of data of radar-only tracking through the FAA's standard tracking system. And we see here an aircraft that was coming down and then passed across, and we missed one detection there when things were slightly tangential. And this is, I believe, about where Atlantic City is, so you've got big buildings competing, and you're just not gonna, the radial velocity of this target's smaller than the radial velocity of the building tangentially. But you only miss one detection and the target will coast through it. The extra spacing in this target track says this target is moving faster. And what we see here are cars leaving the FAA test center, and they leak through the system. That's something else to worry about. And when the detections coming out of the systems tracker are very close together, that means a slow-moving aircraft. And what we have here is a slow-moving aircraft that goes back and forth. And this is what the analog PPI display within a minute or two. I mean, the rain runs 20 miles an hour. This was a very, very heavy rainstorm in August of '75. It was about the toughest one, and we sent a test single-engine aircraft up, and it was essentially unity blip scan ratio in the test. And you can see that the rain is spread out. It's bimodal. and it's 20 to 30 dB above receiver noise level, and we see no false alarms from the rain, but yet we see near unity detection of the targets. And we see some stuff leaking out that are, nobody's perfect. See if I find another there and there. But this is a far cry from what the performance of the FAA's test radar, the FAA's operational and their newest version of MTI radar that they were using at the time. If you're interested, well, one of the references at the end of this chapter describes the MTD processor, and then the other one shows the comparison of the MTD with a co-located, using the same antenna, an ASR 7 or 7 or 8, I believe it was a 7, with the latest version of the MTI system that they were going to hopefully get into the field with a radar video digitizer RVD, the 4th model. Excuse me while I scratch my eye. And you'll be able to see side by side. They were taken at slightly different carrier frequencies, which would have no difference on the data, but exactly the same. They were normalized, of course, for this exactly the same power, but the only difference was you have MTD and you have 3-pulse canceller, and followed by a non-coherent integrator, and then into the same tracker in parallel. And then so you could compare them and see where the differences were. Needless to say, the FAA put this processor into the next generation system, the ASR 9. Now here's actually what it looked like. It's ridiculous when you think about it. Here are it was high tech in those times. Here's the I and the Q, A to D converter, 10 bits. The one on the top is the Q. You can see we appropriately magic marked it. And these are now, you can buy far greater sample rates and linear dynamic range with all the characteristics in a chip. And here's the input memory where the data from pulse to pulse is stored. It's called the corner turning memory. And here is the MTD processor. It's about 1,000 TTL integrated circuit chips, which were the off-the-shelf good chips at the time. You could go buy them. And above you see here a couple of layers. This is what you call software modifications done in hardware. When we first built the processor, it was built with what we thought should be the right number of bits here, there, and everywhere. And we put it together, and it didn't perform exactly the way we wanted. So we had to add certain different numbers of bits in certain places and change some of the constants and algorithms and things around. And what we did is, rather than have this, it couldn't physically be pushed back in. We put a little, Bill Drury, the genius behind all the digital processing here, he put an extension vertically upward with a board you can see here with wire wrappings on it. And then down here is the Clutter map, which used rotating drum technology. And with the 2nd generation MTD had solid state memory. And here's the analog IF chassis. But you could actually put it in a rack. And then there were power supplies for the chips up here below this. Now, one of the points I want to make, and this is about the Doppler spectrum of rain, is that rain clutter residue that leaks through the MTI canceller is correlated from pulse to pulse. And non-coherent integration of correlated clutter is less efficient than uncorrelated clutter. If it's uncorrelated, here's the probability distribution of a single pulse. If it's uncorrelated, this is what the sum would look like. And up here, you'd see the probability of false alarm. And if it's uncorrelated, it goes up here, and you see that this is a smaller area than this area under the blue in this, or you have to lower your detectability to get the same probability of false alarm. It's not the way to do it. This is a graph taken from Fred Nathanson's book, which I haven't seen since then, but it tells the juice about correlated clutter. If you take the standard deviation, the variance here, sigma v divided by lambda times, also divided by the PRF, and this is dimensionless units. When you're up here, you're completely uncorrelated. And when you're way down here, you're completely correlated. So if I have, say for instance, if this number, if for the 10 pulses for the S-band 2D radar in rain corresponds to that, for the PRF and the width of the dot of the rain and the S-band frequency corresponds to that dot. If you have n pulses and you integrate them, what you're only going to get is an equivalent number of 4. This is a log scale. Approximately 4. You're going to have a 3 dB loss due to the correlation. And it is widely not, I've never heard other people bring it into, at lectures or symposia or whatever, go back to this. This is in this region, you're independently sampling. In this region, things are dependent sampling region. And Fred did this calculation and put it in his classic textbook that was written in the 70s. Okay, the first couple of versions of the MTD were designed and built for the FAA by MIT, and they've been extensively documented. Skolnick's third edition, if you want, he has a whole section on it. It's in the radar handbook. You look at the radar books behind me, and it's in most of them that were published after 75 to 80, and just about all of them. After operating the MTD-2, these concepts were employed in the specifications for the 9. And I'd like to reference John Taylor and his colleagues that gave an excellent paper on additional improvements that they made, particularly in the post-processing algorithms, to make the ASR 9 an even better product for the FAA. Remember those cars and the filter design? They did some really cute things, and so I want to give credit where credit is due. That was before Baltimore became Northrop Grumman, and they were Westinghouse at the time. They did a great job, and that paper is documented in reference 15. And these concepts are, as I've said, they're in just, almost all the low PRF ground-based radars, and they've extensively influenced the Doppler processing in other domains. If people choose to build radars that don't have 10 pulses per CPI, the Doppler side lobes go up, and you have poorer rain performance. In summary, the MTD proved that for the first time, digital signal processing hardware and algorithmic technology could be implemented straightforward manner. In other words, doing the job it's supposed to do, to give reliable data to the radar data into the radar beacon correlator for the safety of the traveling air passengers. And solving this particular problem has been a catalyst for the application of this approach to many other civilian and military radar problems. And people told us, you'll never make 1,000 ICs that are wire wrapped together work. And there's some very famous people that said that. And as I said, you can put in a half a dozen programmable power PC boards now, and we did make the 1,000 ICs work. I was a member of that team, and but just the junior most member of the team. I just got out of, I was 4 years out of grad school and transferred to the lab from MITRE. And one of the things people said, well, that drum isn't going to be reliable, that memory drum. And we would pick it up and drop it 4 inches on the floor. Still work. And so you can do these things quite readily. And it solved that low PRF signal processing problem to the target to state problem in a wholly integrated manner, especially handling the tangential targets. I'll give you one very interesting anecdote that Ed Mewey told me when he was visiting in the early, about 1970. They called it the Common IFR Room, and it collected the radar and beacon data from all the radars in the New York area. You know, Kennedy, LaGuardia, White Plains, all of those radars were all integrated together in this big hub. And Ed asked the head air traffic controller, that's like the gunnery sergeant, of all the air traffic controllers doing the work. He says, how do you guys handle rain? And he says, oh, we don't have any problem with rain at all. And he took Ed over to the air traffic control display, and he just took this knob and turned it down. And it said gain. And Ed said to him, well, you don't see any aircraft. And the guy says, yeah, but we don't see the rain. That was the state of the art before this came about. And they see the rain when they want to. And they've since added, the MTD has added a weather display mode, and we've gone on to next rad radars doing the job, and microburst detecting radars. So there's been a lot of progress made in that area. This is the summary of the MTD portion of the talk. Now I'd like to talk about the MTD clutter map techniques. Clutter maps are a memory which store for each range CPI cell in the radar's coverage the value of the noise in the clutter echo. And they are implemented using a recursive filter that updates them in time. Every scan of the radar, the value stored on the disk, and this is the algorithm. It's called a one-pole recursive filter. Excuse me. You take the amplitude that was stored on the disk in the n-1th scan, and you take, well, if n is equal to 8, you take 7/8 of it, and you add to it 1/8 of the new value. So what it's going to do, as rain comes in to an area and moves at 20 miles an hour relatively slowly, originally there was noise, and the A sub n's are all at the noise level. They will build up in time with scans as the time-changing clutter moves in. And this is used to make detections where there's no radial velocity, but the target is above the noise level. They're used to detect targets whose radial velocity is at or near 0, whose backscatter echo is greater than the clutter or noise stored in the clutter map. And the clutter map channel offers a method of detecting targets that are not detected by the subset of Doppler filters that are adjacent to 0 Doppler and whose shape is designed to strongly reject ground clutter echoes. And that's why you saw in that view graph back there, here, that's why you saw here excellent detection. And here, when you're tangential, there was only one dropout, which a tracker can readily hand out. With an MTI system, there'd be a whole band of dropouts, and then you'd have to reestablish a new track. And here, when this aircraft took a turn, there were no dropouts when the aircraft was tangential. And with MTI circuits, that is a major problem. Okay, now the clutter detection techniques use temporal thresholding techniques. The spatial CFAR would detect the edges of moving rain clouds and move up. And a detection is declared if the size of the average coherently integrated return is m times the previous scan's value. So you add up all the pulses, just coherently add them up for that you get in from from before you do any filtering. Just add them up, and if average them, and if you're 4 times what's stored on the map, you say, yep, we got a target tangentially. And that clutter map was implemented for 350,000 cells. These are the range CPI cells. And then you got another 8 Doppler cells. And an additional point, this technique makes it possible the detection of tangential targets flying near large discrete pieces of ground clutter, so-called interclutter visibility in the literature. I forget who was the person at Raytheon. It wasn't Dave Barton. It might have been Schrader or it might have been Ward. But they wrote a really good paper, or it could have been Dave Barton, on interclutter visibility, and it was published, given at one of the conferences. And I hopefully, it'll be in the radar handbook, it'll be referenced. And radar, it'll detect aircraft that moving tangentially to the target, tangentially to the radar, are given large specular echoes, and that enhances, they give off very large specular echoes when they're tangential, and that enhances this detection mode. Okay, and then to the area of post-signal processing clutter map techniques. Even with these relatively sophisticated signal processing techniques, stuff comes through. It happens. And excessive false alarms do occur, and these are when they occur. Heavy bird migration. I showed you a picture of a movie of very heavy bird migration in clutter. Ground clutter whose echoes exceed the dynamic range of the A to D converters, automobile traffic, and other sources. And more sophisticated area CFAR techniques, similar to the clutter, have been developed. Some at Lincoln Laboratory, and those and others that are in that Westinghouse did are in the ASR 9, and they are employed before the tracking function. And good places to learn about these post-processing techniques are in reference 6, these pages, and in reference 11 and 12. Okay, now we're getting along to about an hour's worth of time that I've recorded. So what we're going to do is we're going to take a break here, and then we're going to move on.